Thank you, Bob. Good afternoon, everybody. Obviously, good morning to the other worldwide people. What I'll try and do, thank Nigel initially, of course, for an excellent presentation on describing the actual process. What I will try to do was to give you some of the practicalities that we find actually using the process. I actually work for Merlin Circuit Technology. They are based at Deeside in North Wales, and we have 4 other manufacturing units within the Falcon PC Group in the UK, and 1 company which acquires PCBs offshore in larger volumes. As Bob mentioned earlier, we do a lot of work at our facility to try and help and assist in the technical aspect of the plating of ENIG for our sister companies, but also we do a lot of checks on Asian-based product as it comes into the country through our Kestrel. Initially, the process control of the ENIG process, like all other soluble surface finishes, starts at the copper preparation. This is after outer layer strip etch strip and prior to solder mask application. There are a mixture of mechanical brushing or chemical cleaning solutions available. At Merlin, we tend to use a low pressure pumice with nylon bristlebush scrubbing for the copper surface preparation. We have used this for many years and it's proved very, very successful. With certain exotic materials like PTFE, where you cannot use any brushing or you'll destroy the adhesion properties for the solder mask, or very thin boards which could be damaged in a brushing operation, then we use chemical cleaning. The photograph on the left hand side shows a typical times 2500 on pumice brush surface. This gives excellent adhesion for the solder mask and works extremely well, even for the aluminium wedge wire bonding finish. Electroless nickel tends to have a self-leveling effect during its plating of the 5 microns that we would normally plate on the surface. But if you get the copper surface 2 course, especially if you're doing the same process for all surface finishes, i.e. if you use things like immersion silver, then you do not want a coarse copper surface prior to applying immersion silver, or you will get solderability issues. Aluminium wedge wire bonding, of course, benefits from a very good smooth surface to get the best pull strengths. During the initial use of Electroless Nickel Immersion Gold, in particular in my recollection throughout the UK, there were many problems experienced by most of the fabricators. This was basically an attack of the hot nickel solution, which started to attack the edges of the solder mask and started to break the adhesion. There were many solutions advocated, but what we found was the most popular one, and this was touched on by Nigel, that we part cured the solder mask and then we performed the Electroless Nickel Immersion Gold and then we fully cured the solder mask. We thought this was excellent, of course, but unfortunately what we didn't appreciate that we were leaching sulfur compounds into the actual nickel bath. And on the right hand side of this slide you'll notice there's a table which is extracted from a PC Fab magazine article which gives excellent investigation results from this type of problem. Again, I'm not sure, the first time I've actually done this, anybody can't get hold of a copy, if they could maybe let Bob know and I will arrange to send that forward. The typical problem that occurs in practice is quite visible on the photograph on the left hand side, which shows the actual areas where the solder mask would start to lose adhesion around the actual pad areas. What I've done is I've, on this particular slide, showed you all the process sequence, 23 in total, that we use in a McDermott process in North Wales. We do use Atotech and McDermott chemistries within our facilities in the UK, and both are very successful. We have excellent results from both, but you'll notice from Nigel's description there are one or two slight differences with the McDermott process that we use. So what I'll try and do is similar to Nigel. I will go through the process sequence and try and point out the practicalities that we encounter. We, as usual, start with an acid clean. The most important things that we use this for are to remove any sort of oils, fingerprints and any other contaminants from the copper surface. The important thing are laboratory solution checks, which we do on a regular basis. We use SPC to actually chart the results, and then what we're looking, of course, are for trends and to see whether we can improve by either extending the actual test or looking to turn around and try and bring in the upper and lower control limits. What we have found, and you'll see this as a typical comment all the way through, is temperature is very important on all these things, and temperature is constantly monitored. And the important thing, a lot of the solutions run very hot, and you always lose a lot through evaporation. And the important thing is not to do large top-ups, but to do small, frequent top-ups on a regular basis. Second process, micro-etch. I think Nigel had got 2 microns of copper. We tend to remove 1.5 microns of copper, and we're looking there, of course, to get a good chemically clean copper for the subsequent processes. Again, the checks we perform are laboratory solution levels and also temperature. Notice that we've all got the same slide, I think, just to demonstrate the problem with entrapped micro-etch solution. This is typical. Nigel explained it beautifully, and I'll leave it at that. Obviously, the copper ions in solution from the micro-etch cause the problems with the nittle. Basically, what happens, we tend to find, is that the actual nittle starts to deposit at a much thinner rate than what we have in a normal pad. And it's not unusual to see nittle thicknesses on microsection analysis on skip plating to roughly about between 1 and 3 microns. Again, at that level, it's porous and copper migrates through. The photograph on the left-hand side is typical of what you would see from one of today's circuit boards. There, in BG areas in particular, you tend to find that the designer specifies that he wants the pads flood coating and maybe possibly some form of plug or tent on the top side of the board to ensure no paste wick away. This tends to be the end result. Depending upon the drilled hole sizes, not all the actual solder mask will tent fully all areas. And as you'll probably notice, there are variations on each one of the residual solder mask. And in particular, the one I indicating with the arrow at the moment, is absolutely classical of what will cause you skip plating. As you probably notice, exactly what Nigel said, that every pad that's attached to that wire hole on that same net will almost certainly be affected in the same way. And typical of what we see in practice on the photograph on the right-hand side is this is typical of a skip plating pad and what it looks like on a circuit board when presented to final inspection. But we'll cover that a little later. Our next one is a palladium catalyst. Again, well described by Nigel. Fairly easy, not a problem process. The only issues that we have with this one is probably removing the catalyst from the areas that we don't want it on. And the sulfuric acid post-rinse, again, slightly differently described in the Atitech chemistry, but does exactly the same job. What we're looking to do is to eliminate the problem of a palladium catalyst actually wicking. On the right-hand side picture, you will see the actual wicking of the catalyst which hasn't been removed, and subsequently, of course, nittle and gold will deposit on top of it. And if you look at the photograph on the left-hand side, you will notice that the microsection, as you see through there, the half hole, you can see a lot of the glass bundles have actually picked up with nickel and gold. This should be non-plated through as a tooling hole. We find this problem has been worsened by the use of lead-free laminates, which curing agent is now Novolac, a phenol compound, rather than the old dye-secured types that we've been using for many years before. The old dye-secured laminates were tended to be much more soft and malleable, but wouldn't stand the heat, of course, as good as today's Novolac cured. And although the heat resistance is there, it has a tendency to make the resin system much harder and a little more brittle, and does tend to cause little fracturing of the glass bundles and worsens this problem. And coming to the most troublesome issue of the whole of the ENIG process, Electroless nittle. It causes a lot of problems. It runs hot, approximately 90 degrees centigrade. There are a lot of problems in particular with the amount of metal turnovers, again described well by Nigel. And what we tend to find is as you use the bath longer, of course, it can build up more contaminants. And what we're looking to try and do is when the Electroless nittle, the first thing that you tend to see as a problem is the Electroless nittle will start plating out onto the floor and the sides of the actual bath walls. Then, of course, we have to pump out very quickly, and we have to use a hot nitric acid to dissolve that plated out nittle. It's absolutely essential that when we've done this that we don't damage the tanks, and we don't leave any traces of the nitric acid left in the tank, or the new solution, of course, would not work very well. Again, important that evaporation losses are topped up very frequently, and of course what we have to do is to make sure that all the replacement drums which feed the dosing pumps, again, do not run out. Any imbalance at all in this process will turn around and the bath in one form or another will fail to work. The actual palm controller, which was what described again by Nigel, automatic dosing is essential. To try and control it by normal chemistry checks and additions is extremely difficult. The automatic control is absolutely vital. And we just ensure, of course, that the nittle and pH analysis, we don't just rely on the dials on the units, we actually check that separately, of course, with the chemistry laboratory. Always make sure that solution is being circulated and the replacement pumps are delivering in a 1-to-1 ratio. Absolutely essential. What we use are rate panels to control and verify the plating thickness. Rate panels are accurately profiled out pieces of laminate where we etch off the copper, so they're just base laminate, and we process them down the line with a jig or fixture full of normal production panels. What we do after the nittle plating operation is we remove those rate panels and we weigh them. The weight of the panel initially, obviously, we subtract that from the read weight panel and we calculate the nittle plating thickness. What we do with the rate panels, we store them, and to try and ensure that we're getting everything consistent, McDermott technical representatives will select samples randomly and forward these to their German laboratories for confirmation testing. What we're trying to do is to ensure that we don't let anything at all that could sort of result in a black pad situation end up on our customers. Although the high metal turnovers reduce process costs, it has been shown that nittle baths operated at high metal turnovers are more prone to hypercorrosion of the nittle surface during immersion gold plate. Now, this we've read in numerous technical articles and also proved during trial studies that we've done in conjunction with McDermott in our own facilities. And what we're also finding is the increase of bath contaminants could be partially responsible. we are hoping that the ASPIS project that Bob had mentioned earlier, that Professor Martin Goosey will be presenting later, we are also a part of that project, and of course are looking forward to doing anything that we can to supply samples to see if we can prove some of the theories. One of the classic problems that we also see, and this could be from boards manufactured in Asia or Western Europe, is what we call nittle creep. Nittle creep is typical, as you can see with the two red arrows on the left-hand photograph. What it's done, the nittle has extended from the side wall of the track and along the base laminate and then started to rise up the solder mask sidewall. On the right-hand side there, then what you've got, of course, is it hasn't managed to reach it that far. Typically on the left-hand photograph, even without any solder mask dams, you still get this potential problem of the nittle creep on both sides. What we tend to find is, with the solder mask dams in the centre, and in particular with a little undercut that you can see on both sides, it can be that residual palladium has actually caused the problem for the nittle to metallize. What we do tend to find though with modern lead-free laminates, the copper profile, as you can see a little on the right-hand side photograph here, can be extended from peak to trough, and we're actually seeing quite often peak to troughs of about 8 to 12 microns. If the etching operation on the outer layer is not quite adequate, then you can leave small little tips of the copper dendrites from the copper foil in the actual surface of the laminate. What we also find is that is another process which tends to cause problems with nittle foot. And transferring the actual baskets between Electroless nittle and the immersion gold tank can also be quite critical. Must be take extreme care that drip and drain times don't allow any drying out of the nittle surface. What we tend to find is it appears to passivate very, very quickly, and although the gold will plate on top of it, you tend to find that you get a black pad type of appearance when trying to solder to it. The other thing we should do is rinses should also not be too excessive, or that can also cause problems. Immersion gold again runs hot but doesn't create too many problems. Mainly the standard laboratory solution checks, but nowhere near, of course, as problematic as the Electroless nittle. Most important thing for the immersion gold, again as stressed by Nigel, is not to leave the panels in too long. You don't want to get too thick a gold deposit on, otherwise you get too much hypercorrosion. And just one quick one there, an immersion gold drag out, of course, to try and save cash on the process, is what we do, use a LabMaster pump filled with ion exchange resin and continuously circulates the actual drag out solution to try and reclaim as much as possible and keep costs down for customers. Other typical potential problems that we see are breakdown of work basket protection coating can result in extraneous ENIG deposits which become detached from the baskets and tend to adhere to the adjacent board. It can also be caused, of course, in more rarer cases by residual palladium activator which has not been fully removed. But most of it does tend to come from the actual basket. As you can see here, typically, although there's no damage to the actual basket coating, we can see on the separator bars at the bottom there are ENIG deposits all the way in each the bottom of one of them, and if these aren't cleaned regularly they can become detached and do adhere quite easily to adjacent panels. Moving over to the basic quality and operator tests, what we're looking for, solderability department, of course, would do solder float, edge dip, rotary dip testing, MUST2 tests are done, which are also complementary MUST2 tests are done by McDermott in their German laboratories, just to double check our findings. The process operator would do tape tests, These will be standard on the metal and on the solder mass, just to make sure that we haven't had any problems with the damage of the adhesion of the solder mask, and to ensure, of course, that the metal, both the nickel and the gold, are adhering properly to the copper below. What we also do, XRF measurements are taken on the rate panel and on sample boards. Now, although these are spot checks, we do tend, of course, to rely heavily on the XRF measurement for the thickness deposits. Surface cleanliness is done by the quality department, and we do standard ionograph testing. The actual gold strip test, which was mentioned by Nigel, we tend to do this quite regularly. Again, we have a setup permanently in place, and we run it at 20 grams per litre. We use a Degussa gold strip of 625. We have done a lot of trials to check whether we are damaging the actual nittle surface underneath when we strip the gold, and so far we've found a process which we know actually works extremely well. And when we strip it, we can look at the gold surface and review the nittle just to make sure there are no signs of corrosion. The process operator will also check for any rinse water drying stains or extraneous electrolytic nittle immersion gold flecks on the board surface using low magnification microscopy. On the gold strip test boards, we subject them to our maximum visual magnification, tends to be between 1.5 and 2,000 times. If there's any indication of any nittle surface corrosion, what we do, we will then forward the board to a local laboratory, Quantum Micromet in Buxton, and they will perform ESM and EDAX analysis for us. These are typical photographs of what they will find. On the left, of course, no hypercorrosion at all, exactly what we want to see. Moderate hypercorrosion in the centre and serious hypercorrosion on the right. Again, I think what Bob was alluding to, if we look at the cross-sections of those, what you're looking at on the left-hand picture are no corrosion spikes at all. Of course, if we're looking in the centre one, excuse me, what we're looking at there are some form of corrosion, probably down to about 20–25% within. This board's still soldered, and it's soldered okay, but obviously it would be very worrying to look at that. On the right-hand picture, what we're looking at is serious hypercorrosion, and you can see on here there are some of the actual fissures go down through to the copper, and when this was done under EDAX, then we did find copper peaks on the surface. Exactly what Nigel described, the copper does migrate through onto the surface of the nittle. Typical, again, very similar. I think Nigel and me have been copying here. We've got the typical must wetting balance curves. As plated, excellent solderability, very quick wetting, works well. Of course, after 3 reflows, what you tend to find is the wicking times do tend to extend a little. But the solderability does remain, but it takes longer to wet. But if you want to do any sort of refurbishment of that surface, say for argument's sake, if you've got a lot of boards that you decide you needed to stove to remove moisture, because they've been in the stores a long time, then 10% sulfuric acid clay will remove most of that problem on the surface and revitalise the boards back to good solderability again. On the final slide, what we find is the odd problem that's always one of our sort of worries tends to be the odd skip pad or odd couple of skip pads, etc. So what we do at final inspection, we utilise the Quinn scanning system to actually detect any of those. What it does is we have an image from a perfect board, and then we scan all against it. Any discoloration is found immediately and highlighted, and hopefully we can make sure that there are none of those ever go to the customer. I think I've tried to catch up a little bit on time, and thanks very much for your attention, and I hope obviously it gave you some degree of practicality problems that we experience on a daily basis.
Thanks, Dennis. That was great as usual, and I'm looking forward to getting those microsections to do the SEM work on, because they're some of the best practical examples